Hello and welcome once again for another ES340 video. This is day 17, example problem 1. So today we'll be doing an example of exergy balance, but as usual, we can't forget other things that we've learned in the course, so let's jump to it. So air enters a turbine operating at steady state, obviously key term here, with a pressure of 75 pound-force per inch squared, a temperature of 800 degrees Rankine, and a velocity of 400 feet per second. At the turbine exit, the conditions are 15 pound-force per inch squared, 600 degrees Rankine, and 100 feet per second. Heat transfer from the turbine to the surroundings takes place at an average surface temperature of 620 degrees Rankine. The rate of heat transfer is 2 BTUs per pound of air passing through the turbine. For the turbine, determine the work developed and the exergy destruction, each in BTU per pound of air flowing. And we're going to let the dead state be 40 degrees Fahrenheit and 15 pound-force per inch squared. Okay, so this is obviously going to be, all of these details are obviously going to be important. The first thing it asks for is the work developed. And so the easiest way to find the work, of course, in this case, is going to be using the energy rate balance equation. So obviously at steady state, we know dE dt is equal to 0. So because of that, we find that 0 is equal to Q dot minus W dot plus, this is just a single turbine, right? So it just has a single inlet and a single exit. So that means that we can reduce the equation to the single inlet, single exit case. Now, of course, if there's multiple inlets, multiple exits, you have to account for them. But in this case, we can just simply take a single mass flow rate, which is fine here. So that's going to be equal to m dot times H1, which is the inlet, H2, which is the exit, plus V1 squared. I'm going to call this the volume, not the volume, the velocity, excuse me, because this is the velocity squared over minus V2 velocity squared over 2. And there's no change in height information if you examine the problem, so we're going to ignore the potential energy term. So I'm not writing it in here, but that term obviously does show up, and it just happens to be 0 in this case. We don't have any information about the height, so we assume it's not changing. Okay, so this is what we have, just like normal, similar to any problem that we've dealt with before, and we're interested in the work developed, which is the W. So W dot then is going to be equal to Q dot plus M dot times H1 minus H2 plus V1 squared minus V2 squared over 2. And we can obviously then divide through by M, and notice that it asks for it in BTU per pound. So when it asks per pound or per kilogram or whatever the mass might be that it's asking for, that immediately indicates that it's probably a good idea to deal with quantity W over M or Q over M, or whatever as the case may be. H1, not H2. Okay, so that's going to be my equation here, and we can actually find all of the details by looking through. So the rate of heat transfer is 2 BTU per pound. And the heat transfer goes from the turbine to the surroundings. So that's a key detail here. So because of that, that's going to be minus 2 BTU per pound. Okay. We have to remember directionality does matter here. So the heat transfer is going from the turbine to its surroundings, which means it's negative. Then the next piece, of course, is finding the H1 and H2. Which we can get off of A22, table A22E. And H1 happens to be 191.81, and H2 happens to be 143.47 BTU per pound. So basically, as it enters, it has a pressure of 75 pound-force per inch squared and a temperature and 800 degrees Fahrenheit. And then this one obviously is whatever it was at the exit, which was 15 and 600. Okay, and that's what those values pop out as. This is obviously for air, so because it is for air, you only actually need to know the temperature, right? When we're dealing with ideal gases, we only need to know the temperature. But it's good to be in the habit of writing the pressure, temperature, or whatever, the two, because obviously things like water, propane, and the refrigerant 134A, in those cases we need two intensive properties in order to determine the simple compressible state of the system. Okay, so that's also in BTU per pound. However, of course, as usual, we run into the problem when we do have, say, the velocities, where we have to do some kind of conversion in order to get the proper unit. So we want BTUs. The first thing is that we need to get this in terms of pound force, and then the second thing is that we need to get it in terms of then BTU. Okay, so the relevant conversion factor is 1 pound force is equal to it's equal to roughly, this is rounded, of course, but 32.2 pound times foot per second squared. So that's the first key conversion that we have. And then the second one, because we obviously need to get it into things in terms of BTU, is that 1 BTU is equal to 778 pound force times foot. Okay, so those two key conversion factors are going to help us here. So what we're going to end up with is we have 400 squared minus 100 squared feet per second squared, feet squared per second squared, excuse me. That's going to be then divided by 2. And if we want, we can then rewrite to get it out in terms of BTU per pound. What we're going to end up doing then is doing our little let's divide through here. So 2 times 32.2 pound, well, foot times pound, it doesn't matter which way I write it, right? Foot times pound per pound force second squared. And then this is going to be times 778 foot pound force per BTU. So we can see like the pound forces here go away. This becomes feet squared, which cancels with those two. And then per second squared, which cancels with that. So we're left with BTUs per pound. So we got out to the correct units, right? Because the BTUs are going to come up into the numerator and we'll get our BTU per pound. So I'm going to take that and I'm going to plug that value in. So plus this value up here. Okay, so now we've done the conversions, and this comes out to be approximately equal to 49.33 BTU per pound. So that's my W dot over M dot here. And again, remember that the reason we were able to make this simplification is it's a single inlet, single exit, right? So we have to be careful in the cases where we have multiple inlets and multiple exits. So don't think that it only works out this way for all cases, but most of the cases that we'll see will mostly deal with single inlet, single exit problems. Now for the exergy destruction rate, well, the first thing is remember the exergy destruction, and I'm denoting E to the X as being the exergy here, destruction rate, that's equal to T naught times sigma, right? But we don't know what sigma is. And by the way, what we were asked for was again in BTU per pound, both of them. So what we're really going to be looking for is over M dot. Right, so the exergy destruction rate in this case, I guess this is E dot, right? From the notation from the book, it's going to have a dot on it. That's what we're going to be looking for. So what we can do though is go to the exergy balance, and remember at steady state, for the exergy balance, we're going to have dE to the x here, dt is equal to 0. And we also know that dV, where this is volume now, dt is equal to 0, right? So those terms will drop out of the exergy balance equation. So I'm not going to bother writing them. But the exergy balance equation then looks like 0 equal to the sum over B, we may as well call it, of 1 minus T naught over TB times Q dot minus W dot, and then plus, obviously, this is a single inlet, single exit case again, so we can write out the useful terms. So it's going to be H1 minus H2. Thankfully, we've already gotten that one. minus T naught times S1 minus S2, and plus V1, where this is the velocity, squared minus V2, where this is again the velocity, squared over 2. Okay, so some of these terms we've already actually computed out. If you held out like this term, for instance, this term, for instance, we've already determined. We also already determined the H1, which was up here, the H1 minus H2. So we can obviously use those terms directly in direct. We can figure out those terms directly. I forgot one key piece of information though. This is going to be minus ED dot, right? And this should have been an M dot here. Forgot my M dot. So we have the minus the exergy destruction rate, which obviously then we can rearrange this so that it's ED EX dot D is equal to all of this. To save myself some writing. But now we can actually simplify this equation because we know we knew what W dot. Let's divide through by M dot. So E D X dot divided by M dot is equal to, and let's actually figure out what the sum is. There's only one heat transfer that's happening here, right? So, and the temperature that it's happening at was given up here, 620 degrees R. So we know that that's our TB. Okay, that's our that's the temperature at which the heat transfer is happening. So what we're going to be left with here, is going to be 1 minus T naught over TB times Q. I think I should have written this as QB here. But times Q dot. And we know what T naught is, and we also know what TB is. Minus W dot, this is over M dot, both of these terms, plus H1 minus H2, and plus V1 velocity squared minus V2, this is the velocity, squared over 2. I'm writing these terms in this way at the moment because I think it's convenient. Minus T naught times S1 minus S2. Okay. And the reason that this is convenient is, remember, we actually had up here the W dot written as Q dot over M was equal to, over M dot, was equal to Q, I don't know why I'm writing 8 there, Q dot over M dot, plus H1 minus H2 plus V1 velocity squared minus V2 velocity squared over 2. That was my W1 dot over, or W dot over M, and this is the since there's no additional work terms that are being developed here, this is the total work, obviously. So you can actually see that in this case, a number of these terms are actually going to get canceled out by having this minus sign. So let's actually multiply this thing through just to make it easier to see. So we know that this term is going to be q dot over m dot minus t0 over tb q dot over m dot. And now you can see I have the q dot over m dot term. The q dot over m dot term, this term, and this term. And then I'm going to be subtracting all of those off, minus q over m dot, blah, blah, blah. So that actually simplifies my e dx dot over m dot. You could have actually kept all of the numbers, right, and substituted them in, but this is nice sometimes to just simplify the equation here. This is going to be equal to minus t0 over tb q dot. All of the rest of the terms except for the minus t naught s1 minus s2 are going to get canceled out. So that's what I'm going to be left with. Basically then this is going to be the same thing as this, t naught s2 minus s1, right? And so then now we have this written in a nice way. So that means that we can then, the fact that air is an ideal gas, that's s2 minus s1, is going to be equal to s circle of T2 minus S circle of T1 minus R times the natural log of P2 over P1 so we can make this substitution in here. And what we find is S circle of T2, I just need to remind myself what T2 was. Go way up here. T2 was 600 and T1 was 800. So 600 degrees ranking minus S circle of 800 degrees ranking. I'll just put in the temperature there. Which means that we can find these. S circle of T2 is equal to 0.62607 BTU per pound degree ranking. And S circle of T1 was equal to 0.69558 BTU per pound degree ranking. And then we obviously have the P1 and P2. P1 was 75 and P2 was 15. They were in the same units, so I'm not going to bother with those units. So if you substitute all of those values in, and then obviously we had the heat transfer rate, which was minus 2 BTU per pound. The minus sign still applies there, which is obviously going to cancel that out. And T naught was equal to 500 degrees ranking. That came from here, right? The T naught here came from there. 40 degrees Fahrenheit, which is 500 degrees ranking. approximately, obviously. Where did I see that? Okay, so that's going to get substituted in here, and obviously TB was the 620 degrees Rankine. Okay, so we have all of those values, and if you substitute those all in, then what you should find is Ex dot over M dot, ED, I guess, dot, is equal to approximately 22.01 BTU per pound. That's all that I have for this video. Hope to see you again soon.